This week, you're going to be performing experiment 2, specific heat of substances. So what is specific heat? Well, it's the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Now, based on that definition, do you think that specific heat is an intensive or an extensive property? Remember when we talked about this, an intensive property is one that depends only on the kind of substance, not the amount. An extensive property depends on the amount of substance present, so things like mass and volume. The intensive property that we talked about earlier this semester was density, right? So which one do you think it is? Right, it's an intensive property. Therefore, we can use this to identify a substance, much like what we did with identifying the unknown metal by determining its density earlier in the semester. In order to identify an unknown metal using specific heat, of course, we will actually need to experimentally determine its specific heat. So how do we do that? Well, in order to understand how we're going to do that, we need to have a full comprehension of the relationship between the heat gained or lost by an object and its specific heat. Okay, and that's defined here. So Q equals mc delta T. So Q equals heat, m is equal to the mass, C is equal to the specific heat, and delta T is equal to the change in temperature. So if you say this out loud, the heat gained or lost by a substance is equal to the mass of that substance times its specific heat times the change in temperature for that substance. Okay, that develops this important relationship between the heat gained or lost and the specific heat. Now, if we want to use this to determine the specific heat of an unknown metal, we run into a problem. Okay, we can determine the mass of the metal easily. We can determine a change in temperature, right? We can use a balance for the mass. We can use a thermometer or temperature probe for the change in the temperature. But the specific heat's what we're looking for, and Q, the heat gained or lost, can be difficult to quantify directly. So we need a way around this, and we can come up with a way if we revisit the law of conservation of energy, right? And that's that energy is neither created or destroyed during a normal chemical or physical process, but instead is conserved. So if we have a piece of hot metal here that is cooling off, as it cools, what happened to that heat, that energy in the form of heat? It didn't just disappear, okay? It's not destroyed, it flows into the surroundings. So what we need is a way to capture that heat and therefore be able to relate that back to how much heat was lost by the hot object. Since it is neither created nor destroyed, but is conserved, if we can quantify how much we've captured and relate that back to how much was lost, we will be able to circumvent this problem of not being able to come up with a Q value directly. So let's see what I mean. Okay, so we got energy that's being lost to the surroundings when you have a hot object. What if we put it in water? When we put it in water, that energy in the form of heat flows into the water. If we know the mass of the water, the specific heat of the water, and the change in temperature that water undergoes, then we have a substitute or another form of the heat gained by that water. Remember, Q equals mc delta T. This means that the energy lost by the hot object is equal to the energy gained, heat gained, by the water. Right? It's not going to disappear, so it has to go from one thing to the other. So another way we can write this is minus Q of our object is equal to Q of the water, where minus indicates that energy is being released and the positive indicates that energy is being absorbed. So the heat given up by the hot object is equal to the heat gained by the water. And since the heat gained or lost is equal to mc delta T of the object or substance, the mass, the specific heat, and the change in temperature, we can substitute that in for the Q, thereby circumventing the Q value. Okay, so we now have the mass of the object, specific heat of the object, and the delta T of our object. The mass of the object, that's easy enough to measure, so is the change in temperature. Same thing with water. In both cases, the change in temperature and the mass are fairly easy to measure. The specific heat of water is actually a known value, something we can look up, and it comes out to 4.18 joules per gram degree C. Well, that's great, right? The only unknown here is the specific heat of our object, which is what we were looking for. So we can rearrange to solve for it and just calculate our specific heat of the object. Well, our idea is right. The principle of what we're talking about is correct, but our system is not accurate enough to perform this calculation because we are losing heat to the surroundings. There's nothing to stop the heat energy in form of heat that flowed from the hot object to the water to then flow from the water to the surroundings. So the amount of energy that we capture in the water is not equal to the energy that's given off by the hot object. So we need to revise our setup a bit. We need a way to prevent the energy in the form of heat from escaping to the surroundings. We need to use something that insulates. So we'll be using what's called a calorimeter. A calorimeter insulates from the surroundings. It will prevent heat loss. It is not a perfect system. Of course, some heat still will be lost, but it's so minimal that we can negate it and still get accurate results. So we're going to put our hot object and our water in this calorimeter and prevent heat loss to the surroundings. However, we now have to take into account that the calorimeter itself is also absorbing heat. We can stop at that point, but we have to include that. So our equation gets modified a bit and now becomes minus Q of the object, the heat that's given off by the object, is equal to the heat gained by the water and the calorimeter. From there, we substitute in our MC delta T for each Q. So mass of the object times specific heat times delta T, and same thing for the water. Now when we get over to the calorimeter, there's a small difference, right? Where did our mass go? Well, we don't need a mass in this term, and the reason is that this C-cal is not a specific heat. It's unfortunate that your lab manual chose to use the same letter for the calorimeter constant, which is the C-cal, as it does for the specific heat, say something like water. The specific heat really just means how much energy does it take to raise 1 gram of a substance 1 degree C. The calorimeter constant, on the other hand, is saying how much energy does it take to raise the calorimeter 1 degree C, not 1 gram of the calorimeter. So since specific heat is on a per gram basis, we have to have a mass term that's included. For the calorimeter, since it's for the entire calorimeter, not on a per gram basis, we don't include a mass. However, this means that the calorimeter constant that is determined is specific for a given calorimeter. So once you determine the calorimeter constant for your calorimeter, you need to use that calorimeter throughout the experiment. Okay, so no mass there because that's not a specific heat. It's a calorimeter constant. It's a different thing. Okay, so don't get confused there. Otherwise, it's just MC delta T. Another point I should mention is that the delta T of your calorimeter is equal to the delta T of the water. So imagine that you have no hot object in here yet. You just have some cool water, you have your calorimeter, and it's sitting on your bench top. If it sits there long enough, it equilibrates at the same temperature, which would be room temperature. Right? So the water and the calorimeter are at the same initial temperature. Then you take your hot object, put it in your calorimeter. The temperature of that system will slowly increase until it reaches an equilibrium temperature, and at that time, the calorimeter, the water, and the hot object are all at the same temperature. When you do that, okay, the water and the calorimeter end up at the same temperature, they start at the same temperature, therefore their change in the temperature will be the same. Okay, so we take our expression here, we can rearrange that to solve for specific heat of our object. All right, which is what we're looking for. All these values can be determined by monitoring the temperature during this process and recording the masses that are necessary, so the mass of the hot object, the mass of the water used, except that we don't know the calorimeter constant because we haven't determined it yet. However, we should all agree at this point that once we determine the calorimeter constant, we could plug that into this equation and easily solve for the specific heat of our object or metal. Okay, so how are we going to determine what our calorimeter constant is? Well, we can use a similar method to what we've just looked at, but instead of using an object that's hot for which we don't know the specific heat, let's use one for which we do know that value. So instead, let's use hot water. Okay, we know the specific heat of water is 4.18 joules per gram degree C. And so, if we use hot water, we will know our specific heat of our hot object. The only thing we won't know is the calorimeter constant. Same type of equation, we're just solving for a different variable. Okay, so we have our hot water that we're pouring into our calorimeter. With our cool water, we're monitoring the temperature through this process, and then the temperature will increase until it reaches an equilibrium value, and that will be our final temperature for everything. Okay? We'll also need to know the initial temperature of our hot water and the initial temperature of our cool water in order to solve. So the Q of the calorimeter is equal to minus Q of the hot minus Q of the cool. And this is just a rearrangement of the equation we've been seeing. Right? Another way you could write this is minus Q of the hot water is equal to the heat gained by the cool water plus the heat gained by the calorimeter. This has just been rearranged. So we plug in our MC delta T for the different Q's, except for the Q of calorimeter, which has no mass term. It has a calorimeter constant instead of a specific heat. And we rearrange to solve for our calorimeter constant. Right? The mass of the hot and cool water, easy to determine using balances. The change in temperature we can get from our monitoring of the temperature. And the specific heat of cool and hot water are the same, 4.18 joules per gram degree C. So we can solve for our calorimeter constant. And just one more reminder that the C-cal is a calorimeter constant, not a specific heat. That's why the Q-cal does not have a mass term. So we've got our calorimeter constant by substituting in hot water instead of a hot object for which we don't know the specific heat. That allows us to determine our calorimeter constant. So the first thing you're going to do in lab is determine your calorimeter constant using this method. You'll do 2 trials of that. After you've calculated your calorimeter constant, you can use that in conjunction with the 2 trials using a hot object instead of the hot water. You'll be able to utilize your C-cal to calculate the specific heat of your object, which is what we're looking for. After you've got the specific heat of the object, you'll compare that to known values for different metals, and hopefully you'll be able to determine the identity of the metal that you're working with. Let's look at the actual experimental setup that we'll be using. Okay, now you'll notice our calorimeters are very, very fancy, very, very high-tech styrofoam coffee cups. They actually work quite well for our purposes. Okay? So just make sure that your cups don't have holes or tears in them or anything like that. And you will have 2 cups, one nested inside the other with a lid. That's going to serve as our calorimeter. Then you'll notice that we have a temperature probe set up that's hooked to our MeasureNet station. Now the station, using this temperature probe, will monitor the temperature as we go through the experiment, and it will plot data points very, very often, giving us beautiful data, assuming that you're performing the experiment correctly. So we've got our temperature probe in here monitoring the temperature of whatever's going on in the calorimeter. So if when we're determining the calorimeter constant, we would have cool water in here, be monitoring the temperature, and then we pour in our hot water. The temperature would go up and then eventually stabilize at some equilibrium temperature, okay, and then we'd be done. For the second part of the experiment, where you use the hot object, you would start out with cool water in here, and then you're going to have your hot metal that you're heating up in a test tube in a hot water bath. Now notice the thermometer is in the metal. It should be centered from the sides, a certain distance from the bottom as indicated by your lab manual, so that it gives us an accurate temperature reading of the metal in the test tube. Once that gets to the desired temperature, as indicated in the manual, you'll take this out and you will pour the contents of the test tube into the calorimeter while monitoring the temperature. Of course, as the hot metal dissipates its heat to the surroundings, the temperature that you're measuring will slowly go up and eventually equilibrate, right? And that'll be your final temperature for measuring the specific heat. Some things to keep in mind for this experiment. Your calorimeter does consist of the 2 styrofoam cups. You have to use the same calorimeter throughout the experiment. Right? Once you've determined a calorimeter constant, that is for that specific calorimeter that you use to measure. So you have to stay with the same calorimeter throughout. Masses of the water, as you've seen, okay, are very important. So if you spill any, if you splash any out, that's going to cause errors in your final measurements. When you're putting that thermometer into the test tube containing your unknown solid, right? So if we go back where we've got our thermometer here in the test tube, you can either try to ram your thermometer into the solid, which will end up in a broken thermometer, okay? We like to keep our thermometers in good shape, so please don't do that. Or we can do this method kind of illustrated here, where if you have your metal in your test tube and you turn the test tube on its side, right, the metal will coat the side. You'll be able to easily insert the thermometer exactly where you want it, and then when you turn it upright, the metal will fill in around the thermometer, and you'll have a perfectly centered, perfectly adjusted thermometer without breaking it. Okay, so make sure you use this method when putting your thermometer into your metal solid. It is very important that you follow the amounts and temperatures given in the manual. Okay? Failure to do so can result in bad data. For the hot water, and this is probably the biggest problem that you can have in this experiment when determining your calorimeter constant. When you've heated up your hot water and you're ready to add it into your calorimeter that has the cool water in there, you're told that you need to have a specific amount, forget what it is, let's say it's 50 mils, and at a specific temperature. Well, the common mistake that people make is that they will measure out the correct volume of water, then heat it up, okay, and then pour it in. Well, as you're heating it, you're losing volume. So you want to heat it first, then you want to transfer it to a graduated cylinder so that you have the right amount. And the last thing you want to do immediately before adding it to the calorimeter is to check the temperature using a thermometer. So you check the temperature. You've already started your station recording the temperature in your calorimeter. And as soon as you take that temperature with the thermometer in the hot water, you pull it out of the graduated cylinder and you pour that hot water into your calorimeter. The time between when you measure that temperature and you transfer in the calorimeter has to be minimal if you want to get good values for your calorimeter constants, which then will influence how good the values you can get for your specific heat. Okay? In fact, you should be getting calorimeter constants well below 100 joules per degree C. So a benefit of being able to do the calculations before you come to lab is that when you get in there, you'll be able to determine whether your data is giving you good calorimeter constants or not. Okay, the lab manual indicates that you should use 25 by 200 millimeter test tubes. We're going to be using 18 by 150. They work just fine, okay, and you'll be checking those out from the stockroom. And then the book also says to use between 15 and 20 grams. You're going to want to use 20 grams for this to work well. Okay, so make sure you use around 20 grams, not 15. Okay, and then as always, be safe, have fun, and enjoy the chemistry.